In this video, I'm going to show you two examples where we are going to approximate the area of a region bounded by two curves using rectangles and then finding the exact area using the definite integral definition. Okay, so here I want to approximate the area of the region bounded by f of x equals negative x cubed plus 2 and the x-axis, so I'm bounded above the x-axis. On the closed interval from -2 to 1, I'm going to use 5 subintervals and left-sided rectangles. So we need to have all of this information before we start our problem if we're going to approximate. We need to know the function and then where its boundaries lie. So its boundaries are with the x-axis, this closed interval. We're told 5 subintervals and we're told what type of rectangles. I'm actually going to also show you how to at least set up if I have the right-sided or the midpoint rectangles and how you would find all those corresponding function values. But we're going to go through all of the steps from beginning to end using the left-sided rectangles. After that, we're going to do the exact same problem. So if our problem is posed like this, find the area of the region bounded by, this is the same curve we were given and the x-axis on a closed interval. Notice how we're not given any other information. We're told to find the area. That means we're going to find the exact area. We're not doing approximation. We don't know how many subintervals. We don't know what type of rectangles. So that's the difference between whether I would be approximating, we would literally be told we are approximating, or whether I'm finding an exact area. All right, so here's my graph. I just printed it out, and let's go through all the information again. So we have the curve. This is negative x cubed plus 2, so I'll even write that on there so we have it handy. We're on a closed interval from -2 to 1, and we're bounded with the x-axis. So let's talk about the boundaries. So I know that my first boundary is between the curve and the x-axis. So it's not always necessary to draw this boundary, but I'm going to just for emphasis. I'm also bounded between -2 and 1. So I'm going to draw those boundaries as well. Notice how I stop when I'm up to the function because that's my last boundary. So I'm looking at everything shaded, I actually didn't need that part, between -2 and 1. So I'm going to stop there at 1, and the x-axis. So that is the area of the region that I'm looking for. We're told that we have 5 subintervals. So that means n is equal to 5. So the first thing that we need to find is the width of each of those subintervals. Remember that's delta x is equal to b minus a over n. So in our case, we have 1 minus a -2 divided by 5. So the width of each of my rectangles is going to be 0.6. Next thing that I'm going to do is mark off how wide each of my rectangles are. So starting at -0.2, I'm going to move 0.6. So that will bring me to -1.4. And again, this is just an approximation. We know this isn't going to be perfect. But I'm going to mark all of those x values for the widths. From -4, again, we're moving another 0.6 to the right, so that's going to bring me to -0.8. Moving another 0.6 to the right, I'll be at -0.2. Then I'll be at 0.4. And then lastly, I'm going to finish up at 1. So I'm going to draw up to the function height so that I could see my 5 rectangles. Now we're told to draw left-sided rectangles. So that means I'm getting the function height from the left side of my rectangle. So if this is the first rectangle here, from -0.2 to -1.4, I'm going to go to the left side of that rectangle. And I'm going to draw across until I get to that right boundary of my rectangle. And then complete it. That's my first rectangle. Again, remember when we're building this rectangle, sometimes we'll have a little bit of over approximation. Sometimes we'll have a little under approximation, depending on the shape of the curve and the type of rectangles that we're using. Okay, we're going to do this again for the second rectangle. Go to the left side of it, move across till you get to the right side, and draw down. The next thing that we're going to need is the function value at each of those rectangle heights. So since these are left bounded rectangles, right, we're looking at this height right here for the first rectangle. This is determined by finding the function value at the left endpoint of the rectangle. So I'm going to need f of -2, which when I calculate that, it's going to be 10. The second rectangle, the height comes from here, f of -1.4. Again, remember to find the function heights. I'm just plugging x into the function here and finding what that value is. So at 1.4, it's 4.744. Okay, so those are our first few steps. We took the number of subintervals, found the width of each rectangle by finding this delta x. Then we marked off going from left to right every 0.6 units, since that's how wide each rectangle is. Then I built my rectangles. Since they're left-sided rectangles, I started at the left, moved across till I got to that right boundary of that particular rectangle, and then completed it. Moved to the left, completed it, moved to the left, completed it, and I went all the way through till I got my 5 rectangles. After that, I found the function height, because remember, we're going to have to find the area of each of these rectangles. The area is easy because that's just multiplication. So having all this information ready for you makes life a lot easier. So when you're doing this problem, if you're not given the graph like I just had it printed out for me, you're going to draw the graph or draw it on your calculator and then sketch it on your paper. And these are the steps that you should be taking. You should sketch your graph, mark off your boundaries, find your width, then create your rectangles, find your height. The rest is easy. The rest is addition and multiplication. So the area of this first rectangle, again, you could find this within the picture. You don't even have to do it in the big formula if you don't want to. I need to find the area of this rectangle. Well, the area, remember, is the length times the width. Well, my length, we know, is 10. My width, we know, is 0.6. So 10 times 0.6, the area is going to be 6. Second rectangle, the length is 4.744. The width is 0.6. So the area is 2.8464. Again, don't round anything. If you're not asked to, here we were not asked to, so I'm going to keep everything as its exact value. So I have 6 plus 2.8464 plus 1.5072 plus 1.2048 plus 1.1616, and I get an area of 12.72. Now, if I were doing this problem and I was asked to find right-sided rectangles, we would be doing the exact same process. So the width doesn't change. The width comes from the number of rectangles and the interval. So my width is still 0.6. And now let's talk about how to build the right-sided rectangle. So just as before, instead of going to the left, we're going to start with the right boundary of that rectangle. And then we're going to draw across. So here is the first rectangle if it's right-sided. Again, go to the right boundary, draw across. Okay, so again, just like we did before, to find the function height in this case now comes from the right boundary. So this is going to be f of negative 1.4. The height of this one, f of negative 0.8. So the only change in the process is how we build our rectangles, because that's going to change the function height. Okay, so we would still find all those function values, find the area of each of those rectangles, and then add up all those areas. Now the last case is when we have the midpoint rectangles. Difference with the midpoint is that the height comes from the middle of the individual subinterval. So if I'm between -2 and -1.4, I need to go in the middle here, which is going to be -1.7 to get the function height. The function height comes from here. So I'm going to draw my function height and then again complete my rectangle where I need to. So we notice that with this type of rectangle, there's a little under approximation, a little over approximation. And as we saw in the lesson, that when we have the midpoint, it is a bit of a better approximation because it's going to even out those over and underage. Are my rectangles with the midpoint. So again, the function height comes from the midpoint, f of -1.7, f of -1.1. That's why it's so important to graph it and have everything marked on your graph, because it just makes this part so much easier. And then just as before, find the area of each rectangle and add them all up. Now, in the last part of our problem here, I asked you to find the exact area. So here I have the integral from -2 to 1 of x cubed plus 2 with respect to x. So x to the 4th over 4 plus 2x, evaluating from -2 to 1. -2 to the 4th over 4 plus 2 times 4 minus 1 to the 4th over 4 plus 2 times 1. Here I'm going to get 16 over 4, which is 4, plus 8 minus 1/4 plus 2. So I have 12 minus 1/4 plus 2 is going to be 9/4 is 39/4, which is about 9.75. If we go back to our approximation, we saw visually that this approximation was definitely over what the actual area is, and we got 12.72. So our approximation makes sense with what the actual value is.